So I wanted to talk about paging. The idea here is that we're going to take our physical RAM and we will partition it into fixed size blocks, which we're going to call frames. And the frames are going to be a power of 2, usually someplace in somewhere from like half a kilobyte up to 16 megabytes. And we're going to, mentally at least, we're going to be logically partitioning our memory into blocks of the same size called pages. We're going to need a way to keep track of which of the frames are currently being used by a process and which ones are not. And the idea here is that we'll be allocating, when a process needs to run, we'll allocate a number of frames of memory to hold the contents of that process, the data, the code, that kind of stuff. From the process's point of view, its logical address space is going to be referring to pages rather than to frames, and we'll get into how we map between the two in a little bit. So here's kind of one way we could look at our physical memory. So here I got a very simple piece of memory. So we'll say that our entire memory consists of only 16 words. Typically, by the way, the phrase word refers to the smallest piece of memory that you can access with an address. So anyways, in the left-hand column here we have what the physical addresses would be. Because there are only 16 words of memory here, our addresses are going to run in binary from 000 all the way up to 1111. And I just put some letters over here in the right-hand column to show these are the contents of the memory. Maybe just put the letters of the alphabet in there or something like that. So if we go ahead and we partition this physical memory into frames, let's say that each frame consists of 4 words. So a power of 2, very small power of 2, but 4 words. And so then I basically just wrapped a black box around each of the different frames of memory over here. And on the right-hand side here, I've basically labeled the frames. So the first frame is frame 0, then frame 1, frame 2, and frame 3. Still have our same physical addresses listed over here. But of course, once they're split up like that, what you'll notice is that the frame number over here corresponds to the first 2 bits of the physical address over here. So that is, if we sort of split those off, you'll see that the first 4 words, the frame number is 0. And for the next 4 words, the frame number is 1, referring to frame 1. And the next set of 4 is 10, binary for 2 is the frame 2 is referred to there, and so on. So basically you can go ahead and we can split or consider splitting our physical address, in a sense treating the high order bits as the frame number and the low order bits as an offset within a particular frame. So for example, this address, let's say here, this physical address corresponds to frame number 1, and your offset 2, but in binary, 2 from the beginning, that's a 0, 1, 2. So that's this chunk of memory here. This word of memory is what this physical address 0110 refers to. Okay, so now we switch over to talking about pages. So the main idea behind paging is that we allow each process, rather than using a frame number like this, you have a page number. But the pages are the same size as the frame, so what we're really doing is we're mapping, sort of arbitrarily, our pages onto the frames, although they could occur in different orders. So frame 0 could hold a page, frame 1 could hold a different page, frame 2 a different page, and so on and so forth. And this basically then just talks about the same idea from the logical address point of view. From page numbers, you take whatever your logical address is. Again, you kind of split it in half like we had before in our previous example. The left 2 bits were the frame number, now they're the page number, and the right 2 bits are the offset within that page or within that frame. So what we need to do now is come up with a way to map from the page numbers to frame numbers, to actual physical addresses. So from the point of view of a process, let's consider a very simple process that needs only 8 words. That is, it needs 2 frames, or in our case, 2 pages worth of memory. So from the process's point of view, its logical address space looks like this, just a continuous sequence of numbers from 0 down to 8. Well, 0 through 7. We have 8 words that we're trying to access. If we go ahead and we split the addresses into the 2 parts just like we had before, the 2 higher order bits will become the page number, and the 2 lower order bits will become an offset within that page. So here could be an example page table for our process. What the page table does is the index, the page number serves as an index into the page table. So page number 0 is going to refer to the 0th or the first element of the page table, which is the 1. And the values that are stored in the page table are frame numbers. So what this particular page table here says is that page 0 in our process is stored at frame number 1, and page 1 is stored in frame number 3. So then the conversion from a logical address, our logical address space like we just looked at before over here, it's nice contiguous numbers over here, will get converted. What we're going to do is we're going for each of the page numbers over here, we're going to use those as an offset into the page table, as an index in the page table, and we're going to take the corresponding frame value and replace the page number with the frame number that's over here in the page table. So all these 000s here get replaced with 01s over here, and all the 01s over here, because the 1 is an index to frame number 3, they get converted into the 3s over here. So the physical addresses into the RAM that correspond to the logical addresses are shown on the right-hand side over here. Now, one way you can look at this is here's the entire RAM shown again. So we have all of our bits here, and again, we have our 4 frames. Each frame holds 4 words. We have our physical addresses just like we had before. But what you can see is that since our process's page 0 is held at frame 1, so I kind of wrote that down over here. This frame is holding the contents of process's page 0. And likewise, the frame 3 is holding the contents of our process's page number 1. So that's just a very simple example of how the conversion from logical addresses in a paging system to physical addresses works. Now, as long as using powers of 2 like this for the sizes of our frames and our pages, it's really easy to do the conversion of a logical address to a physical address, because all we have to do is we go ahead and we take the page number, we split that out of the logical address, we use that as an index into our page table, take out the corresponding value for our page number, which should be a frame number, and all we have to do is paste those bits back in, basically overwriting the uppermost, the higher order bits that were our page number now become the frame number, and the resulting value over here, at least considered as a binary value, is the actual physical address, and now we can go access a particular word of memory over here and see what we have to see. So the actual process of doing the mapping isn't particularly difficult. And this is basically just a similar example from the textbook to what I just showed you from my Excel spreadsheet diagrams. But same idea, you've got a process over here that now consists of 4 pages of memory that it needs to store itself. And so its page table will only have 4 entries in it. So the pages are numbered 0, 1, 2, and 3. And the frames that are used to store those pages are shown as the contents of the page table. So you can see here, for example, that page 2 is stored in frame number 3. So here's our frames listed over here. Here's frame 3 right there. And yes, the contents that we actually store in the memory there are the contents of our process's page 2. And here's an even larger example, kind of spread out again, where you show here's from the point of view of the process, it's logical memory, just 16 words of memory here running this way. Each page consisting of 4 different words of memory. And here's the corresponding page table over here. And again, we kind of show how the contents of the pages are laid out in the actual physical memory itself in the RAM. And of course, the thing to take away from this is that the memory that the process doesn't have to be contiguous. So you can see here, for example, the first page is down here from addresses 20 to 23, and the next 4 words are from addresses 24 to 27, but then we're kind of back up here to address 4 through 7 for the next page, and so on. So the pages can basically be scattered any sort of willy-nilly anywhere we want in any frames. They don't have to be consecutive each other or contiguous or anything like that. All right, now with paging, you have the possibility for some fragmentation because the memory is always going to be allocated in these discrete sized chunks, whatever you decided your frame size is supposed to be. So in the example shown on the slide here, we'll assume that a page is 2 kilobytes. And it turns out the particular process we're working with here is about 72 kilobytes that we need. So if you work out the math here, divide 72,766 by 2048, you'll find that we need 35 completely full pages, but then the last page, the frame that we allocate to hold that page, is only going to be about half used. We're only going to need 1,086 bytes of that space. So the remainder of that last frame is going to be wasted. It's going to be internal fragmentation. And you can see here that's going to be about 962 bytes that we've allocated to the process that we didn't really need to, but because of the paging scheme, we had to do it. So in the worst case, our fragmentation would be the size of our process would be just 1 byte larger than an even multiple of the size of our frames. And so then you'd have just 1 byte of the last frame would be allocated. On average then, you could say over a large set of processes, you'd expect to waste about 1/2 of the size of a frame for every process that you had in the system. So if you wanted to minimize internal fragmentation, you might think, okay, so I'll just make the frames very small. If the frames are small, then I'm wasting only 1/2 of the size of a very small frame. And that might seem like a good idea, but the problem with that is if you make the frames very small, then the number of frames in the system is going to get very, very large. And that means that an individual process may occupy a great many pages, remembering pages and frames are the same size. If you have a lot of pages, then that means the memory that you have to use to store the page table for that process will also get much larger. And now you're wasting memory just holding the page table. You're not actually holding the contents of the process, its data or its code at all. Because processes are typically pretty large, a lot of modern operating systems actually use different size. They provide different sizes of frames. So they may have a set of sort of small pages like 8 kilobyte sizes, and then much larger pages, 4 megabytes, 8 megabytes, whatever. And then when you need to allocate memory for a process, you allocate basically as many big pages as you can, and then a set of smaller pages towards the end. And that way your internal fragmentation stays relatively small because you're only wasting a little bit of one of those smaller pages. All right, so every process needs to have its own page table. Whenever a process needs to get a new frame or a process comes along, we need to allocate the frames for that process's page table. We need some way to keep track of which frames are available. And the book outlines this. I'll let you just go ahead and take a look at that. There's sort of 2 very simple ways you could do it. One is to use basically a linked list of frame numbers as kind of, and the other is to maintain a free frame. You can use basically bits to indicate whether a frame is free or not. So go ahead and look up how to keep track of free frames in the book. Okay, so as I said before, each process typically has its own page table. So when there's a context switch between processes, then we're going to basically maintain 2 registers to reference the page table for that process that's coming into play. So we have the page table base register. That's going to be the address of basically the address of the first word that comprises the table for our process. And then you have the page table length register, which just says how big that table is, how many entries are in that page table, i.e. how many pages does the process consist of. Now, of course, once we're using page tables like this, you can now see that in order to reference a particular memory access, we actually need to do 2 memory accesses. Let me back up here a little bit to my earlier slide. So you can see when we want to access this address, this logical address, the first thing we have to do is go do a memory access just to get a value from the page table. So that's 1 memory access. We then plug in the frame number. We use this as the physical address. So that's our second memory access. So every memory access now actually takes 2 memory accesses. Okay, so that basically means that if we're going to use a simple single layer paging scheme like this, it basically takes twice as long to execute an instruction as it did if we weren't using paging at all. In order to minimize that overhead, it's quite common to use associative memory, sometimes called translation look-aside buffers, TLBs. I like to think of these as content addressable memory or as lookup tables. It turns out that if you can actually wire memory so that, let me back up a second. So the default way that RAM works is that you provide to the memory unit, you provide your physical address on one side of the MMU. On the other side, out comes the contents of that memory. So that's an addressable memory. It's a standard memory that we use all the time. Content addressable memory works a little bit differently. Instead, you provide the content, something that's stored in the memory, and if it is stored there, then you basically get an address comes out as to where that value is stored in the memory. It's like a backwards kind of memory. Now you could actually think of this as like a lookup table. So the idea then is what we're going to store in our content addressable memory is we're going to store our page numbers. And basically what you can do, you can think about the page as being keys into the memory so that when we present a page number to the lookup table, if the page is in the table, then the frame number just pops out. So it's very quick. Now, the problem with content addressable memory is it's very expensive. So typically we can only afford, if we want to keep the cost of the CPU down, to have we can only afford a relatively small chunk of content addressable memory. So our translation look-aside buffers are usually pretty small, kind of as shown on the slide down here. They might just have up to 1,000 entries, something like that. But it's very, very fast. So typically the runtime is going to be like 10% of the amount of time it'll take to access the associative memory will be about 10% of the amount of time it would take to actually go to the RAM and get a value. So it'll be much, much quicker. So our strategy is fairly straightforward. What we're going to do is when we have a page number, we're going to first ask the associative memory, do you have a frame number for that page number stored in there? And if you do, it'll return right away. It'll be very quick. If it's not in there, however, then we get what's called a miss. So the content addressable memory just says, nope, that value is not in here. So in that case, we would have to resort back to our tried and true process, our old-fashioned process of just going to the page table, stored in regular memory, getting the frame number, plugging that out, and going forward from there. So graphically, our process will look like this. We'll get our logical address over here. We'll look at the higher order bits, that's the page number. We'll present that to our associative memory. If the frame number is in there, that is, if there's an entry in there corresponding to that particular page number, the frame number will immediately pop out. We've got a hit at the TLB. We go ahead and we plug that in to the higher order bits in our physical address. If we got a miss because the page wasn't in the table, then we have to go through the whole process. We have to go to the page table, treat the page number as an index in the table, get the resulting value there, which is a frame number, and plug it in. And then finally, we can then go to the physical address. So if we get a hit, that's typically going to be fairly quick. We have a relatively short time. It'll be less time than it would have taken to actually access the full page table. And then we just get our one access over here. So that allows us now to talk about the effective access time. If we don't have associative memory at all, then the effective access time is just going to be 2 accesses using this single table lookup scheme. The first access is to go to get the value from the page table, and the second access is to go now with the physical memory, the address we have, and get a value. So once we add this associative memory, then that's going to change our effective access time. In order to calculate what that's going to be, a little probabilistic stuff here, we need some variables to think about, some values. So let's have epsilon stand for how long it takes for our associative lookup either to get the frame number back or to tell us that the page number we give it is not in the associative memory. And usually that's going to be very fast, less than 10% of the time it will take to actually access the physical memory across the RAM bus and that kind of stuff. The hit ratio is alpha. That's the portion of times that we go to the associative memory and we find the page number there. We'd like that to be very high because if alpha is very high, if it's close to 1, then we're going to basically evade doing 2 lookups, 2 memory accesses. Then we need M, which is the amount of time it takes to actually access the RAM, the physical RAM. So here's a simple example where we're going to let alpha be 80%. That means 80% of the time that we present a page number to our associative memory, we get a frame number back. We're going to let the amount of time it takes to access the associative memory be 20 nanoseconds, and the amount of time it takes to access the RAM will be 100 nanoseconds. So the calculation for the effective access time is fairly straightforward. No matter what, we got to pay the cost of going to the associative memory to see if our page is there. Then there's two possibilities. One is that we find the page in the associative memory, and if that's the case, we only have to pay this cost one time. That's the cost to go to the RAM. On the other hand, this value over here is the proportion of the time that we get a miss in the associative memory. And in that case, we have to go do two memory accesses, as shown over here, one to go to the page table and the other to actually go get the value out of the RAM. So simplify that out and you get this formula down here. If I take the numbers that we plugged in, that I provided up here, and plug them into our formula, then you see we come out with an effective access time of 140 nanoseconds. I will point out, by the way, that this calculation is different than what you find in your textbook. For some reason that I don't understand, the textbook basically just ignored the epsilon value, didn't add it to its calculations, which is really not cool. So I've gone ahead and put those in here. So 140 nanoseconds. Now, 140 nanoseconds is to be compared with the 200 nanoseconds we would have had to pay if we weren't using our associative memory at all. So we're definitely making a saving there, 60 out of 200, which is what, 30 out of 100. So it's the 30% savings. If we up our hit ratio to 99%, which is kind of more realistic, then and we keep the other values the same, then our effective access time goes down to 121 nanoseconds, or almost a 60% savings. So it's the use of the associative memory in this case really saves a lot and gets us close, not quite there, but almost close, almost the same we would get if we weren't using a paging scheme at all. If we weren't using paging at all, we were just using pure physical addresses, then of course our effective access time would be 100 nanoseconds because we wouldn't be using page lookups or anything like that. But so here we're paying a little overhead, 20 nanoseconds, or about 20% overhead to what we would do without paging in order to have paging. And of course we get all the benefits from paging. We no longer have external fragmentation and we don't have to worry about memory being contiguous anymore, and there's lots of other good things about paging. Especially when you'll see when we get to the next chapter with virtual memory, then we can start talking about having a logical address space which is bigger than the physical address space. That is, we can have actually more pages than we have frames. And we have to get that to work, but it's pretty cool when it does.